All right, so it's been a while, and yeah, I've just been kind of busy with a few things, and let's get right into this actually before I give a monologue on anything. So last time I had talked about a mind map, and I'm realizing right now that there was this mind map that I gave to you guys that kind of didn't really go over QFT. It went over many concepts in particle physics, but I think in my mind at the time, I was so focused on those aspects of that intrinsically are related to QFT. This was the last lecture. I'm also on a new software here. I'm on an iPad uh, of QFT. So insofar that those topics are related to QFT, I didn't really provide as big of a picture as I wanted to, basically. So I'm going to add more on to this mind map now. And as I move into constructing more of this mind map, we're going to get into actual details. So here's a bird's eye view of QFT. So we can imagine a field. Maybe looks like this. So here's a field. This is a continuous field at every location in space, and I could have numbers at each value in the field. So say I have 4, 26, 7, and 8. Right, so these are numbers. So this would be a scalar field. Right? So this is a scalar field. Examples of a scalar field include density, for example, density and temperature. So these are examples of a scalar field. I give you any point in space, any point P in space, and you can tell me what the value for the temperature is at that point. Similarly, you can do the same thing with density. Right? Okay, what are some other mathematical objects we might want to consider? Well, we can consider vector fields. Right, so a vector field might look something like this. I have a field. Might look a little bit different than this one right here. Nonetheless, we have little vectors at each point in space. Like that. An example here would be E&M, or electricity and magnetism. I give you a point in space, P, or Q. I can name that give that a different name. We'll call it Q. Give you a point in space, Q. And you could tell me what the components of this vector are, of this vector is right here. Similarly, you can do it at this point or this point. You can do it at any point of your choosing. So that's a scalar field and a vector field. Are there any other mathematical objects? There are actually. So we can consider tensor fields. I'll do tensor fields in a different color. I'll do it in green. Tensor field. Okay, what does our tensor field look like? Tensor field might look like this. Here's our field, and we have tensors at each point in space. Right. So at each point we have a little g mu nu, right? A little g What does this look like? This kind of looks like GR, or general relativity, or special relativity, where we have special relativity is actually more of a vector field. In GR, we have, actually I want to do black. So this could be GR, general relativity, where we have tensors at every location in space. Okay. So, okay, that's all fine and good. How about some other, can we think of maybe some other mathematical objects? Well, of course we can. We'll get into this later, but we have these little guys called spinners, right? So what color do I want to make my spinner? I'll make it purple. So spinner fields. We have a spinner field. What is it? So our spinner field, again, might look, here's an example of a field, again. These are really just arbitrary points in space and in time. And see, I said my spinner was purple. So at each point in space, I have a spinner, right? Okay, and how do I want to, I'll call spinner something that looks like that. Maybe I have these little spinners at each point in space. These little objects right here, I'll call them spinners. Right, and if I just fill this in, I have okay, so what do I have? I have a scalar field, a vector field, tensor field, spinner fields, and we can go on. We can create any object, any mathematical object we want, and we can say that one of those is located at every point in space. Okay. And so what about quantum field? What about a quantum field? A quantum field. So I'll go black again. So quantum field. So what does this guy look like? Well, we want to consider, what does it mean to quantize a field? So what does it mean to quantize a field? And the idea here is that we have, say for example, our scalar field. Here's our scalar field. Right? And then we have another field. We have this is a scale. This is one conformation of a scalar field. So I'll call black conformation 1. All right, and then maybe I'll call red conformation 2. Okay. And then I could keep on doing this for different colors. I could basically have different conformations of the field. So this could tell me, for example, so stuttering my speech a little bit here. So this essentially means this means that we're quantizing the field. Right? We have different fields permeating through all space and time, and each one of those fields has a different conformation. So I'll call conformation 1 here psi of x. This is a function of space-time. This is a function on space. And I'll call conformation 2 here psi 2 of x. And black here is psi 1. And so psi 1 to psi 2, remember these fields are dynamic. They change between conformations. So we can say we have a function, therefore, that sort of takes a single conformation. I'll put the red conformation here. And that maps us to a complex number. Why complex? Well, fundamentally complex because we're dealing in quantum mechanics. So that's going to be a complex number. Okay, so we have this function right here. Oops, that pen is a little too thick. This function right here, this sort of takes a conformation. So this right here is a conformation of some field, and it returns to us a complex number. Now, here's a good way of thinking about it. This is, I kind of came upon this idea of thinking about this idea by thinking that each field here, I'll put another one in. My apologies for any background noise as an ambulance. Each field, here's another one. We're quantizing this field. Each field has a specific conformation, and the conformation again will tell us. Again, I think I misspoke a little bit. These don't evolve into each other; they have different conformations. But each field has a conformation, and what does the conformation tell us? So we have a conformation. This tells us something about the evolution, the conformation of the field, And this tells us something about the dynamics of, particles, or systems. I'll say systems of particles, actually. I'll say system particles, of systems that they describe, systems of particles that they describe. Okay, B. And so we have different conformations. We have, say for example, if we were to if we could introduce, sort of link this notion in with Feynman diagrams. All right, so we have some Feynman diagrams. Suppose we have two electrons. My bad. Suppose we have two electrons. They come in, something happens, some interaction happens, and they come out. This is the end state. And we could say that one of these fields, say the red one down here, say this red one down here, say the red field. So here's my red field. It's going to describe one situation that might happen. So one situation that might happen. Okay, we could have, and maybe for completion here, I'll put a red pen. All right, we could also have a different field describing another situation. So another another situation. That's what our field looks like. And we could do this on and on and on for different conformational fields. So I can do, here's another situation. So another one. Another situation. Or a set of rules, basically, on what's going on. And each one of these situations, or each one of these conformations, is mapped to some number that we can measure. Okay? So, and these are complex numbers. They're not real numbers. Right? Real numbers, there's two real numbers that make up a complex number. We won't quite go into that. We'll just say that's a complex number. And the function that does that is this psi function that I had mentioned right down here. Right, so psi takes in some conformation and it spits out a complex number, a measurable complex number. We can then, so this complex number, say, we can then take this complex number, we can say this complex number is z1, we can square it, we get some probability amplitude. Right, z2, we square that, z3, square that, and so on. So what else is there to QFT that I haven't really gone over yet in this video? I want to touch upon Fourier analysis really quick because I didn't really do that quite yet. Which, by the way, I was reading a little bit more on quantum field theory today, a little bit more advanced stuff. Twistors, these are interesting objects. I'm not too much of an expert on these things, but so I have a twistor field. I've been trying to think about what that might look like. But again, yeah, that's sort of beside the point. Anyways, we could have, okay, so where are we? So we have fields, we have the functions that map our conformations of each field, each quantized field, or not each quantized field. I quantize the field conformations, and then I take a function that maps those fields into a complex number. Okay, so each complex field, or each field, so each one of these guys, so I'll take this blue one. Where's my blue? I think I was using a different shade. Let's use that one. So take this complex field. This is kind of looks like this. So each that has a value might have a vector at each point in space or a scalar at each point in space. It's got a complex shape to it, right? It's got a complex shape to it. Complex shape to it. I'll just say that. This could be a really complex looking field, a really weird looking field. We could say weird, complex, it doesn't really matter. The idea here is that if we actually want to do analysis and we actually want to do some mathematics on this field, there's this idea that this field can be broken down using the Fourier transform into different, more simpler fields. So say I want to break this down into 3 simple fields. Now, it's not just going to be theory. We could, in theory, have an infinite number of modes within this field that make up this field. This is a Fourier analysis. So I'll get back my blue here. The idea here is, okay, this, I'm going to say for the time being, because I can't draw in four-dimensional space, I'm going to just say this is a 2D field. Even though it kind of looks 3D, I'm going to say this is, I'll just call it a 1D field for right now because it'll be easier to draw. But we want to imagine that we can have a four-dimensional or a three-dimensional field. I'll just call this 1D for right now so I can make this look a little bit better here. So we can break this field down into different modes, right? So perhaps one mode looks like this. Perhaps another mode looks like this. And perhaps another one looks like this. Okay. But again, we can abstract our minds a little bit. We can try to imagine these modes, and we can mathematically imagine these modes here in three-dimensional or four-dimensional space. Okay. But again, the idea here is this is Fourier transform. We Fourier transform something complex into some things that are less complex. And here's where the physics comes in. Where the physics comes in when we consider the amplitudes of these modes, right? Or at least some physics comes in when we consider so the amplitudes of these modes is roughly going to be our proxy for the energy, the different types of energies that make up this field, or the different multitudes of energy that make up this field. Okay. So from f of t, or from our Fourier analysis, our amplitudes will give us all the energies. Now you can say, well, okay, what if we have infinite number of energies or infinite energies? Then we go through renormalization process. So this is renormalization, and this is a topic for later as well. Right now, I'm just introducing us to the bare bones. Right, this is I'll repeat myself because I'm not afraid to do that. So the repetition again is we have multiple confirmations. That was the wrong tool. This is the right tool. So we have multiple confirmations. We have a function that takes each confirmation to a real number or to a complex number. Right? These confirmations tells us something about the dynamics. Right? In terms of Feynman diagrams, each configuration can tell us something about what happens in here. And again, we use psi to map to a complex number for each situation. Now this is really, it's complexified QFT in a nutshell. The reason I say complexified is because many people out there, they just say, well, we have we want to communicate quantum field theory to people, but not have it be scary. And so we'll just say there's a field everywhere in space that describes where electrons and photons are, something like that. My intent here is not to do that. My intent here is I don't want to scare you, but we're going to go into these fields. We're going to go into taking a look at confirmations, taking a look at how we can do Fourier analysis on these. And one more thing before I think I'll end this is with this we are also going to be able to talk about when we mention dynamics here, we'll be able to talk about Lagrangians, Hamiltonians, and stuff like that, because this right here is dynamics. And there's a deep relationship between the Lagrangians and Hamiltonians and fields. Fundamentally, what's going to happen is that we're going to have these Lagrangian densities They're gonna they're gonna take the coordinates, or they're gonna take uh, every point in our field. These Lagrangians are going to take each point and the derivative of each point with respect to each other, and it's going to give us some structure to our conformation. It's going to give us some dynamical structure to this conformation. And once we have this Lagrangian, we'll be able to do a lot with it. Right? We'll be able to construct Hamiltonians. We'll be able to do functional analysis. We'll be able to do all this kind of stuff. Right? So all of this, in a nutshell, is sort of the complexified quantum field theory, right? And really, again, when we say quantum field theory, we're meaning this process. We're meaning, okay, we don't have one field like this. We don't have one field. We have multiple fields. We have multiple field conformations, and they live all over the place. And we're going to map each field to a complex number, right? And the physics comes into play when we start attributing Lagrangians to define what these fields are going to look like. Right. I think in the next few videos, I still don't know what the route is I want to go through. I want to go through all this, or explain all this. I think I'm going to maybe take a step back and go over some simple calculations in Fourier analysis, maybe. I still really don't know. There's tons of places to start here, but bear with me as I try to make this as easy as I possibly can to make it understandable for you. So I'll see you guys in the next one. Thanks.